Okay guys, in the previous class I did the example of the inverted pendulum, but that has no integrator in the open loop transfer function, and we added the zeta as a virtual state variable, and at the end so it increased the order of the system to n+1, or 2 + 1 was 3, and we designed the controller. Now the thing is that in reality, like as robotic systems or too many things, so we may see what? Okay. We may see MIMO system, multi-input, multi-output, multi-input, and multi-output systems. How would you control them? Like as robotic system, like as a Baxter Matlab that has 7 degree of freedom system. We have 7 actuators or the DC motors and 7 joint angles. That's right. So now let me give you an example. This is that I had from the vibration course ME5 I'm teaching every spring. Now I'm taking here because this is the LTI system, and this is the system we have. Suppose that you have one spring here and one mass here, one spring here and one mass here, and one spring here, right? So and suppose you have also a damper here, for God's sake, and you have a damper also here, right? So I'm naming it K1, C1, M1, mass 1, K2, M2, mass 2, K2, and the C2. Let me choose recordings, right? Yeah, so obviously this system has how many degree of freedom system? 2 degree of freedom, because you have 2 displacement that they are independent from each other, so x1 and the x2. But your boss says, okay, you have this mass spring and damper system, you design a controller u1 and u2, for example, that the x1 at time infinity goes to r1. Here I say the unit step. That's right. And the x2 at infinity in a long time goes to r2. I'm gonna say 2 unit step functions, right? So these are my desirable set points for this spring and mass damper. These are reference set points which are non-zero. Remember, non-zero. Non-zero. First let me okay, non-zero. I'm gonna do both 0 and non-zero. Okay, clear? So now asking you design a state feedback control law to that happens for both non-zero, these are, and the 0, means x d1 if I release from a non-zero initial condition, and x d2 backs to 0. Understand? So what we're gonna do from dynamics, we have to apply Newton's second laws. Sum of the forces in x is equal to m1 x double dot 1. Sum of the forces f x for 2 mass 2 gonna be m2 x double dot 2. Obviously from here, if you plot the free body diagram, I'm going to do that by another color. So if you, and my assumption is that as I talk to x1 is greater than the x2. If that happens, spring K2 gonna be compressed, that's right? And we have a stretch here. So if you cut from here, and if you cut from here for free body diagram, you're gonna stretch K1, so you wanna have a reaction force from here, K1 x1, and you have a reaction for the spring, which is linear, damper, which is C1 x dot 1, you know, from the vibrations, right? And then because this is compressed, this is gonna give you K2 x1, because you assumed x1 is greater than x2, right? So you have exactly the reverse of this other side. Let me do by this color. So you're gonna have, for this, you're gonna have K2 action and reaction forces, right, from Newton laws. And now this is gonna be compressed. You're gonna have this K2 x2 because it's only affected by x2, and this is gonna be C2 x dot 2. So now for each of them we're gonna do that. So M1 x double dot 1 is equal to, look at this set are gonna be, here is positive, here gonna be negative, positive, negative side. So this is negative, minus K1 x1 minus K2 x1 minus x2 minus C1 x dot 1, and what? External force, the controller that you gonna design for this MIMO system. You have two inputs, two outputs. Two inputs, two control laws, U1, U2, and two outputs, X1 and X2. And then for the mass 2, M2 x double dot 2 gonna be, now I'm gonna look at here, right? Here gonna be positive, K2 x1 minus x2 minus K2 x2, because showing the negative side, minus C2 x dot 2 plus U2. Okay, again, this is not vibration course. We're gonna design these control laws by state feedback. Okay, so if you rearrange everything and summarize, the final equation is gonna be this. I move to other side. K1 plus K2 in x1 minus K2 x2 plus C1 x dot 1 is equal to U1, right? And now M2 x double dot 2 plus K2, this is, guys, K3 by K2, this is K3, so this is gonna be K3 because it's K1, K2, K3, so K2 plus K3 in x2 minus K2 in x1 plus C2 x dot 2 is equal to U2, the controller that we're going to design today in theory and in Matlab, right? So obviously you can rewrite like this, because you have, so each system is second order, that's right, each system is second order. You have two systems, we have fourth order differential equation, fourth order state space equations. How? It is very straightforward. Look at here, you have to, now you set up your state variables to be transferred to the Matlab. You're gonna say, let me see this M1 is x1, displacement of mass 1, and the M2 is, say, x dot 1, as we already defined. M3 gonna be x2, displacement of mass 2, M4 gonna be velocity of that mass. having the time derivative from the both sides, you're gonna have dm1 means derivative is equal to x dot 1. X dot 1 is m2. dm2 gonna be what? X double dot 1. Okay, now dm3 gonna be x dot 2 gonna be m4, and the dm4 gonna be x double dot 2. But we have x double dot 1 and x double dot 2 from here. See? X double dot, x double dot. X double dot 1 is this 1 minus m1 u1 minus, see, dividing both sides by m1 u1 minus k1 plus k2 in x1 minus k1 plus k2 in x1. x1 is m1, so it's gonna be m1. Here we go. Minus k2 x2. The other side is gonna be positive. Positive k2 x2. x2 is m3. m3. See? And minus c1 x dot 1. Minus c1 x dot 1. X dot 1 is m2. So you see that our dynamics is now coupled because you have m1, m3, m2. That's right. And exactly from here the same. 1 over m2 u2. Look at here. u2 divided by m2 minus k2 plus k3 x2 minus k2 plus k3 x2 is m3. Here we go. Plus k2 x1 plus k2 x1. x1 is m1. m1 minus c2 x dot 2 minus c2 x dot 2 is m4. m4. Here we go. So our state space equation is going to be dm1 is equal to m2. dm2 gonna be 1 over m1. This is mass of that. The control design that the control input that we're gonna design today, hopefully, k2 m1 state variable plus k2 m3 minus c1 m2. That you're gonna exactly write this in what? Matlab for this MIMO system. M4. Oh. And dm4 gonna be 1 over m2 u2 minus k2 plus k3 m3 plus k2 m1 minus c2 m4. Huh? So if I write this in the matrix form, why? Because at the end of the day, because this is the LTI system, I'm gonna teach you LTV system if you have time in this semester, okay? At the end of this course. So if so we have to generate x dot is equal to ax plus bu, that's right, or here gonna be m dot, because our state variable at m is equal to am plus bu. So if you do that by saying that your m is what? m1, m2, m3 and m4. So if you do that, you get this m dot 1, m dot 2, m dot 3 and m dot 4, right? Look at here, guys. M dot 1, m dot 2, m dot 4 is equal to, now we have to make this a gonna be 4 by 4 because you have 4 state variables. Gonna be m1, m2, M3 and the M4, right? Now, first line has only M2, so this is gonna be 0, 1, 0, 0. Only you have M2. Second line gonna be, okay, M1 has minus K1 plus K2 divided by M1. So minus K1 plus K2 divided by mass of the first. Second gonna be M2 minus C1 over M1. Minus C1 over M1, right? 3 gonna be K2 over M1. Gonna be K2 over M1. Do we have M4? No. This is gonna be 0. Third line, let me change the color. Third line has only M4. So M4, so gonna be 0, 0, 0, and 1. M4, right? Fourth line gonna be M1 is K2 over M2. So here you have K2 over M2. Here you had K2 over M1. That's right. This is M1. So 2. Do we have 2? No. Here gonna be 0. Right? Here gonna be 0. And 3. Yes. Minus K2 plus K3 over M2. Minus K2 plus K3 over M2. 4. Yes. Minus C2 over M2. Minus C2 over M2. This is your A matrix. This is your A matrix. Plus now your B. Guys, in the CISO system, your B was your B was, remember, for the pendulum or other examples, n by 1 matrix. But when you have MIMO system, 2 inputs or 2 outputs, so the number of the inputs to the system, you have what? You have n by number of the inputs. Number of the inputs, if I say m, here is 2. So and the order of the system is 4. Is 4 by 2. That's right. And this is gonna be U of t. Understand? So let me write like capital like this. Right? Because why am I writing capital? Because I'm gonna explain to you. So I'm freezing, hold on. Okay. So first column gonna be for the mass 1. This is gonna be for mass 2. Okay, mass 1 and mass 2. Okay, now let us look at there. U is the second, is here for U1, for mass 1. Here we go. That's right. So only you have 1 over M1. That's right, in the M.2. So you're gonna have 0, 1 over M1. Do we have any U2 here? No. The rest are 0. 0 and 0. Or second line. Your U2 is here on the M.4. This is M.4, that's right. Or 1 over M2. 0, 0, 0, 1 over M2. Now, let us look at this again. This is not like that, okay? We are not done yet. We are missing some point here, guys. What is that? What is that? The point is that this is 4 by 4 matrix. This is 4 by 1 matrix. The result gonna be 4 by 1. Yes, because our left hand side is 4 by 1. Now look at here. 4 by 2 by 1 gonna be 4 by 2. That sucks. So that's why I made this capital, because your U now is U1 and U2, because you have 2 inputs to the system. If you have 3 inputs, this is gonna be 4 by 3 I'm sorry, whatever, n by 3 in 3 by 1. So now look at here, if I change that as it is, so your u is 2 by 1. Now 4 by 2, 2 by 1 gives you 4 by 1. So if I want to write here, you have to multiply like this, u1, because you are designing two controllers to the system, and the u2. So u1 gonna be multiplied by this column, u2 gonna be multiplied by this column. So this is your B matrix. B matrix. Understand? So, and your C, because multi-input, multi-output. For CISO system, your C was 1 by n. Remember? It was like 1, 0, 0 like that. But here, your C gonna be again, what? See here, guys. M1, M2, M3, and M4. That's right. This is 4 by 1. That's right. Huh? Here you're gonna have 2 by 4 because you have two outputs. So I as a designer of the controller, you are designing. I'm saying I want to observe only M1 displacement of first mass and M3 displacement of second mass. So here gonna be 1, 0, 0, 0. This multiplied by this gonna be M1, and 0, 0, 1, 0. This multiplied by this gonna be M3, and this is your C matrix. You see, that's the difference between the MIMO system and CISO system, or MIMO system we say, and CISO system. So the notations of the B and the C changes because you have multi-input and multi-output. Plus I say D is 0 in U of T. Again, capital. I mean boldface is not capital. Okay? Understand? So you have to, even that when you're dealing with the robotic system, suppose you have a 3D degree of freedom robot. Huh? So you have multi-input, multi-output, 3 actuation and 3 joint angles. So that your robotic system is LTV system. But again, if you want to make it as very simple case as the LTV system by eliminating the Coriolis parts, so your B and C must be like this. Okay, so now having that, what we're gonna do, I'm gonna do this, guys. So I'm gonna do this. I'm gonna say, okay, I'm gonna say first we have to design K. But you know that the trivial things that I taught you was KX, the state feedback controller. But again, as I taught you in the Matlab K, I'm doing it by Matlab because I'm teaching you, but at the final exam, you have to do by hand and then validate by Matlab. Don't jump. Okay? Is Acker or place. I'm gonna say what I write like that. You're going to say A matrix, B matrix, and the J, the desirable poles. For example, for this system, your boss says design a controller for me, okay? Design a controller for me that both masses, when they are backing to the 0 from some initial conditions, okay, be critically damped. Says be critically damp. Critically damp. I'm starting with very simple, that both the x1d desirable wants to back to origin. Okay, remember this is the basic case. So for that, you're gonna say, okay, from the vibration control that we learned from in the SDSU, the real parts of the poles or the eigenvalues must be negative real number. Gonna be J1, so J gonna be, because you have fourth order system, you have 4 poles. Gonna be -2, -3, -4, and -5. Huh? right? Or you can say this -3. Let us examine that. So by having that, let us go to Matlab. Let us go to our lovely Matlab to eventually develop the most comprehensive example for the LTI systems for designing controller. Okay. First of all, I have to generate an M file. Hold on, guys. Okay, so I'm gonna now go step by step for this MIMO system. Okay, so I'm gonna say, so function, as you know, dm is equal to, I don't know, MIME system is t and m, and I said that state variables is here is m. So dm, I'm generating the space for that, zeros 4 and 1, because I have 4 state variables, and say m1, mass of 1 I say is 1 kilogram, and m2 say 0.5 kilogram. K1 is I don't know, is 10. K2 is 20. K3 is 30. Okay. 30. These are that. So C1 damping 1, I don't know, is 2, and C2 that we had was, I don't know, 0.1. Let me do this 0.3. I'm gonna explain why later. Okay, so having this, now I'm going to making your A matrix. A matrix was this. Look at here. Your A matrix was, let me go here, 0, 0, 1 minus K1 on K2. Okay, so it is 0, 1, 0, 0, and minus K1 over K2 divided by M1 minus K1 plus K2 divided by M1, as we have defined here above. That's right. So, and what we have else? Minus C1 over M1 minus C1 over M1. Okay, guys, these are underlined. These are the masses, not the state variables. Okay, and K2 over M1, K2 over M1, and 0. Third line is 0, 0, 0, 1, 0, 0, 0, 1. Yes. And the fourth line is K2 over M2, 0, K2 over M2 and 0. Minus K2 plus K3 minus K2 plus K3 divided by M2, right? And minus C2 over M2, minus C2 over M2. Here we go. This is your A matrix. That's right. Let me double check. 0, 0, 0, 1, 0, 1. Minus K1 over M1. Minus C1 over M1. K2 over M1. 0, 0, 0, 0, 1. K2 over M2. 0. Minus K2 plus K2 over M2. Minus C2 over M2. Here we go. This is your A. Your B, as we said, is you have 4 by 2. So it's gonna be 1 over M1, 0. Look at here. Oh no, 0, 0. 1 over M1, 0. Here you have 0, 0. The second line is that. That's right. 0, 0, 0, 0. And 0, 0, 1 divided by m2. Ooh, m2. This is your B. It's 4 by 2 matrix, right? Now let's go to state equations. The m1 is equal to m2. See that these are not underlined. These are the state variables I'm defining here. The m2 based on equation is 1 divided by m1. So u1 that I'm going to design right now, obviously multiplied. u1 so minus k1 plus k2 minus multiplied by m1 minus c1 divided by multiplied by m2 and k2 plus k2 multiplied by m3. Here we go. This is for that, and that's it, right? 1 over m1 minus m1 c1 m2 k2 m3. So dm3 is equal to m4. I'm writing like this because I'm gonna be consistent with the notes that I developed for you. This is for teaching purposes. For research, I never do that. Okay, so it's gonna be 1 divided by m2. This is mass divided by m2 multiplied by u2. u2 minus now minus k2 plus k3 multiplied by m3 minus c2 multiplied by m4 and plus k2 multiplied by m1. Here we go. Right? So we have this, but the problem is that suppose that I'm writing here, we release m1 from initial position of 0.5 from rest and m2 from 0.8 from rest to go to go back to origin. Remember? Origin. Okay. Now guys, look at here. I say if the back to origin, A is equal to Aker A and B and J. These are our poles. So here I'm gonna say J is equal to, as I said in the notes, -2, -3, -3, -3, and -5. Let me do this in -4. Who cares? Or 3.5. Nobody. So guys, now look at here. If I run this part only, okay, look at here. It says system must be single input. Okay, it says system must be a single input. Why this gives such error? Hold on. Why this is free? Okay, I know what happened. So why that happens? Because here, when you have the MIMO system, guys, you have to replace the Aker command with the place command. Aker command works only for the CISO system, but the place work for what? Work for MIMO system. Say 7 degree of freedom robot. So here we go. See, if I run it here based on what I write out, now you have 2 rows of the gains. One of them is for mass 1, another is for mass 2. That's right. Look at here, guys. Let me this row is for the mass 1, and for u1, look at here guys, because you're gonna have here we had u1 minus k1 in x state variables, and u2 minus k2 in x. Look at here guys, let me show you. So this, where is that? This line is your k1, this line is your k2. Understand? So because you have 2 input, 2 output, you have 2 rows. If you have 3 input, 3 output, you're gonna have three lines. You're like as a Baxter, if you have 7 input and 7 joint angle as output, you're gonna have, if you transfer to the LTV and LTI, you're gonna have 7 rows of the gain matrix. Okay, this is the reality. So where we are, okay, now we have it. That's right. So, but before solving the problem, let me double check everything. So now we got the k. So your u1, gonna be your k first column and all the rows. That's right. First column and all the rows, as I showed here. Where are you? This. By this command, I'm saying this line. That's right. So, come on, come down. So, okay, minus first row and all the columns multiplied by your state variable vector. That's right, m2, m3, and m4. Right? Look at here, guys. As you saw, this is 1 by 4, 4 by 1. Gonna be 1 by 1. The scalar, and you put it here. Here we go. Understand? So let me move this here, because these are when we want to back to origin. And the u2, okay, u2 gonna be the second row of that, second row on all the columns of the k, the gain matrix, understand? And hold on. Okay. Understand? So I saved as meme. That's right, MIMO. Now I have to generate the solver. So I'm gonna say T, and the output capital Y is OD45 at mim. I say run from 10 to 0.1 step time to 10. You have 4 state variables. So, but I told you in the notes, I want to release it from what? From, where is it? Oh, in the code actually. I want to release it from first method 0.5 meter and from 0.8 meter. Say 0.5 meter and 0 and 0.8 meter. That's right, initial condition to go back to the origin, as I taught you previously. Right? So if I say figure 1 plots time and y, first all the rows and first column, and as blue, and hold on, and 3 gonna be third state variable. That's right, gonna be displacement of mass 2, gonna be red, and say line width gonna be 2, line width gonna be 2, and the same for here. Here we go, and I say grid, and I'm naming it as okay, I'm saving it as the meme solver. That's right. But let me debug it first, because I'm doing with you, it may that I have typos, huh? Let me double check with you. Okay, so minus C1 over M1, K2 over M1, 0, 0, 0, 1, K2 over M2. K2 plus K2 over 2 minus C2 over M2. So B is 0. So and 1 over M2. 3 U, first line, second line, 1 U. So if I do that and run it, so let's see what I think I know what's the error is. What? Line width. Ooh. Line width command. Here we go. If I do that, you see that for this MIMO system, if I release from the non-zero 0.5 and 0.8, our controller works and backs to our system to the origin. You see the backs at the 4 seconds, so let me make it bigger, huh? It is for 4 seconds. So now you can design a controller for MIMO system like robotic systems. And say legend, to be clear, legend. This is for mass 1, and the second is for mass what? Mass 2. Here we go. See? This is for the mass 1, and you see that is almost what? Critically damped. There is no oscillation. Why? Because you, as the design engineer, you selected the real part of the pulsar eigenvalues be a negative number, not a real number, not the imaginary number. So if I change it a little and say, okay, you know what, 1 minus 5 and 15, okay, let us see what we get this time. See, this time we get this behavior. Let me run it again. This is gonna be much longer. Why? Because now these are not almost equal, so you are making the overdamp system. That's right. This is the vibration course that I was teaching on the graduate level. Understand? So, and now obviously, if you say I want to have a pair of complex conjugate poles minus I, and for the second mass, gonna I don't know, 2 plus I, for example, minus 2 minus I, obviously you're gonna have this. No way. See? Overshoot. So let me increase it. Here we go. Obviously you're gonna have underdamped system because you have overshoot here. Alright, this is your responsibility, that you design proper eigenvalues of the poles of the system that satisfy your boss demands. This problem gonna be another class or 2 class because it's very comprehensive. Then after finishing this, I'm gonna teach you how to design the observer. Okay, so this class continues this MIMO system design.